Hi, welcome to this talk on reliable command, control, and communications links for unmanned aircraft systems. My name is Jens Finkhaeuser. I wrote this paper that we're presenting here with my colleague Morten Larsen. Just so you're aware, we figured that because this is pre-recorded, it's much easier to have just one presenter in this video. Of course, that means Morten is not going to appear here. Apologies for that. Okay, let's get started, I would say. Okay, so first of all, before we go into the slide, the paper was produced as part of the Comp for Drones project. This is an ECSEL Joint Undertaking project. The link is at the back of the slides. For context, we're not talking about all kinds of drones here. We're in Europe in the European R&D project, and so we're looking at European regulations, and that means EASA. EASA is basing the regulation of some of their drones, some of the types of drones here on SORA, and SORA has different categories of drones, right? And we're looking at the specific category. Specific category is not small toys on the one hand, that you have to fly line of sight with your controller in your hand all the time anyway, and it's not large aircrafts that maybe the military uses and has different regulations anyway. We're looking at the specific category because this allows sort of mid-sized drones, and this allows commercial exploitation, or it can be used for research. And so different criteria apply to how to use them. And one of the commercial exploitation that gets thrown around all the time is the pizza delivery, right? So think mid-sized drones that can carry a couple of pizzas. One of the important factors here for the adoption of this kind of technology that we're talking about is cost effectiveness. In toy drones, we don't need it. And in large drones, we can also afford far more costly solutions. But for these mid-category of drones, we need to find something that actually works from a cost point of view. Lastly, the EASA concepts also include the use space concept of operations. That's sort of the replacement for air traffic management for these mid-sized drones. And it also has to interoperate with ATM. And in here, we have different airspace categories or types. So a flying over unpopulated woodland would be very low risk airspace, but populated city centers are, of course, much higher risk. And then on the highest risk, we have something like airports or nuclear power stations or something like that. And what we're really looking at is providing reliable command, control, and communications links for these mid-sized specific category drones for the highest airspace risk classes. Because on the lower risk class, you might not need that much reliability. Okay, so why do we do this? Well, one of the interesting things here is that if you want to take a drone beyond visual line of sight, and that can mean at large distances or around the corner so that you no longer see it, or also into a building with a gas leak that you have to check out, then you have two larger pillars that support this beyond visual line of sight mission. That's on the one hand the detect and avoid. That's not something we're concerned with. And the other, it's the reliability of the command, control, and communications link, the C3 link. And really this applies to any autonomous mission, right? We can use the pizza delivery as a use case. We can use the gas leak building as another use case. The moment you go beyond visual line of sight because you have to, that's when this applies. And the regulators are understanding this and are starting to address this with their draft regulations. Now, the paper looks at regulations as they exist and might be applied, and I'll go into this in a little bit. Goes into the technologies that exist that could be applied. I'll go into that, and then comes up with a technological proposal. Right? That's the scope for this paper. So let's first talk about what reliability for C3 links means. As I said before, it's always possible to do this with costly bespoke solutions. And we want to avoid this. What we really want to look at is commercial off-the-shelf solutions. And the interesting thing is that there typically reliable under good conditions, right? We know this from our mobile phones, right? Most of the time we can pick up the phone, we can browse the internet, we can make calls, there is no problem. But we also all know that one signal hole, if you go there, you don't get anything anymore. And that's, of course, bad for drones. Now, on some level, this is avoidable by plotting the right path for the drone. But there will always be unavoidable conditions. And really what the problem is in slightly more technical terms is that, well, we either have no line of sight for the radio between the drone and the antenna on the ground, and so that's why communications is disturbed, or some other kind of interference occurs. And we have to deal with this. So how do we do this? Well, with off-the-shelf solutions, it's called a black channel approach. This comes from railway systems. I'll talk about this in a second. Well, not really, it's used there. A black channel approach, which means you cannot control the actual link technology, right? Doing so would immediately bump you back up into the very costly solution, the white channel approach. So you accept the fact that you cannot control the link technology. It might be unreliable, it might be untrustworthy. So you add the reliability features on top of this unreliable link technology. And in terms of redundancy, you do this by supporting multiple links, right? And it could be two LTE links, it could be two Wi-Fi links. Better still, it's a mixture of both. It could be a private 5G link and a Wi-Fi link for very local operations, for example, right? Just 4 or 3, who cares? The number, the sky's the limit. Okay, so we're looking at how to add reliability over commercial off-the-shelf solutions in a black channel approach. And here's an illustration for this. I mean, it's pretty self-explanatory. In this case, you have a drone that has a blue and then a yellow lightning connection to cell towers. It also has a connection downwards to the Wi-Fi router, and it has a satellite connection as well. But you can easily imagine that if it was flying between the buildings, then some of these connections would no longer be available. Okay, so let's talk about regulations. EASA is currently at the stage where it's trying to find the right kind of regulations for this, right? There are the SORA concept and the use-based concept. They are pretty firm already, but within these concepts, they haven't clearly defined yet what the specific requirements are on C3 links to make them reliable so that they match the regulations. They have very high-level abstract keywords right now, which is that they want redundancy, which makes sense. And they want tamper-proofing, which makes sense. So tamper-proofing is you don't want a third actor to be able to send commands to your drone so it crashes into a building, or worse, right? One of the interesting things here is that EASA, of course, looks at projects like such as Comfort Drones, also to understand what the state of the art is and what can be done and what the R&D is, what the direction of the R&D is going into. And so we have this feedback loop right now between we're looking at the regulators, they're looking at us, and we're trying to figure out where the future is basically between us. Now, that's drones themselves, and of course EASA is influenced by air traffic management in this, because that's what they know. Another interesting aspect is railway systems. We know that a lot of railway systems in Europe are actually running over unreliable networks, mostly Wi-Fi. No, and there will be other deployments, but that's what we're talking about here. And they had the same problem in a slightly different way. They only have 2 dimensions, or roughly 2 dimensions to deal with. Their drones aren't, their trains aren't suddenly lifting off and flying into the air. But it's the same class of problems that they want to solve. How to make communications reliable over off-the-shelf solutions, link solutions. And so they refer to standards that then themselves list well understood risks to communications and also mitigation techniques for them. So we're looking at things like message loss or corruption of messages, and how do you deal with this? Well, I'll spare you the details. But we're looking also at the railway regulations, because the way they look at it can also be used to inform how we can deal with the same sort of problems in drones. And the details for that are in the paper. I'll spare you that for now. Okay, so redundancy. We spoke about redundancy is one of the big requirements there from EASA. How we're looking at it is, this is a slightly noisy illustration that we're using in the paper, but I'll run through the highlights here with you. We're using we're looking at the traffic that goes out from the drone or into the drone as, you know, chopped up into different packets, and from a networking perspective that sort of makes sense. And if you look on the left here, we have all these different colored packets of data under the drone, and then they move out from the communications gateway on the drone into this gray box on the left of the middle. There's scheduler there. I don't know if you can read it, the one with the rounded corners, and there all the blue packets get sent over the mobile operator 1, the green ones over mobile operator 2, and so forth. And on the other end of the communications, they're reassembled again. Now, which of these links is currently active, or maybe multiple are currently active, that's sort of up to the scheduler. And the scheduler is really the one that makes the millisecond decision here, or microsecond decision here. I'm getting the message, I need to understand where to send it over this link. At the top, you see another box that says Path Manager. This is really a hypothetical component. Well, hypothetical, we're working on it, but it is hypothetical here in this paper, that makes the longer term decisions, right? That is the one that needs to understand what links currently exist and which are viable because they can log into a network. It can also decide how viable they might be for the foreseeable future because it sees a drop in signal strength, for example. That's the sort of decision making that happens up there. Okay, again, the paper has more details. I'll continue now. So we looked at different technologies. And when I say technologies, we're really talking about networking protocols, because one of the things that all these commercial off-the-shelf solutions have in common is that they are intended to link devices to the internet. So we know that we have an internet connection at some point, and that's IP-based. So really, we're looking at networking protocols that sit on top of IP. And I'll jump ahead to the conclusion and give you, spare you the suspense. We basically have found no technology that really incorporates all these mitigation techniques for drones. And that's an interesting point to elaborate on, because if you look at railway systems like I just described before, you basically have one link technology, right? You're switching Wi-Fi access points, but you're not really necessarily switching Wi-Fi networks. Depends on the implementation, and you're certainly not starting to jump to satellite technology, at least not that I'm aware of. If somebody knows better, please let me know. But what we know from air traffic is that as your plane goes up and down in altitude, different sort of link technologies become available. So for example, we know from mobile networks that the antennas are oriented downwards so that they do not disturb air traffic. And so as you land, you might enter the zone where this kind of link technology becomes available. And as you take off, that goes away again. And one of the interesting things is that these changes in availability coincide with high-risk phases of flight, or critical phases of flight, I think it's called. Starting and landing, that's the hardest part of flying an aircraft. Now, this won't apply completely to drones because they might not fly so high, but the principle applies still, because if you have, for example, an infrastructure of landing pads for your drones, you might outfit each landing pad with its own bespoke and maybe even redundant Wi-Fi routers. And maybe for the duration of the landing phase, what you really want is for the drone to communicate through the Wi-Fi router, because you can sort of guarantee that it's there. So also here, as we approach the landing pad, this link technology might become available, which previously was not. So it is comparable, even though it's not quite the same situation. And so the choice of link technology impacts cost, because satellites, for example, tend to be the most costly link technologies around, at least for the time being. Bandwidth LoRa is famous for not having very high bandwidth, latency, and jitter. And jitter here refers to the variation in latency, basically. So from a certain point of view, what we can say is that our problem here is finding the best link technology for the current phase of flight. So we looked at different protocols that can be sent over these different IP links. And well, the first candidate, of course, is TCP/IP. TCP is used in underlying the web, so it's one of the most widely used protocols there in existence, I think. And it's interesting because it has an extension that's also fairly widely deployed now, multipath TCP, MPTCP. So we looked at that, and we actually experimented with this in previous R&D projects and came to the conclusion that it's very hard to do things well with MPTCP. And some of this is implementation detail, but one of the things that we can also say from research, from past research, is that TCP itself is actually not a very good tunneling protocol. And we want to have a tunneling protocol because we don't really know what sort of application data is going to be sent across our link. And we don't want to know to a certain degree. We want to be agnostic and support all sort of things. Now, there are candidates like Mavlink or something, but we assume, for being future-proof, that we don't know. And so we want a tunneling-capable protocol. And TCP is not good at this. There's something called TCP meltdown, which refers to a cascade of errors that happens when packet loss occurs. Let's leave it at this. The other thing is that TCP itself does not have security. It relies on TLS for security. And I'll get into this in a second. There's a problem with TLS as well. SCTP was invented to fix problems with TCP. And one of the problems it fixes is that it treats reliability of messages a bit differently. And so it can be used for tunneling, which is great. But it also has no security and also relies on TLS. And finally, we looked at a completely different candidate, QUIC. Now, QUIC is the Google proposal that then is currently being turned into HTTP3. And what's very interesting about QUIC is that it takes a slightly different approach to how to deal with connections. But unfortunately, because it sort of is very closely related to HTTP, and HTTP has traditionally been run over TCP, it inherits some of the TCP issues. But on the plus side, it uses DTLS for security, and DTLS is definitely better choice than TLS. Okay, so what am I talking about here? Well, TLS is the industry standard for encryption. We use it when we access any secure website, right? HTTPS means HTTP plus TLS. Now, the downside is that it has a very complex handshake. And you don't want a complex handshake when your link signal is bad, because it might mean you have to resend handshake packages over and over again, and on a bad link that can only cascade to terrible conditions. DTLS is the datagram variation of this. It's a lot more lightweight, which is good, but it shares the problem with the handshake. And the other technology that we wanted to look at is WireGuard. WireGuard is an emerging standard. It's, well, standardized, but it's not everywhere yet. And one of the key features is that it has a very, very simple handshake, which is ideal for our critical link handover phases. Now, on the downside is it gets this easy handshake because it relies on a pre-shared secret. And managing this pre-shared secret is not really great for large deployments. So our conclusion is that we need to combine all these features, right? We need to pick features from SCTP, from QUIC, from DTLS, from WireGuard to make the ideal protocol. And that's what we're currently working towards. So we can provide a virtual link that has all the reliability guarantees that the regulations want. And it's also, well, we haven't really dealt with security yet, but of course we have to add security on from the WireGuard and TLS examples to the protocol as well. And the paper really outlines an approach, a conceptual architecture for making this work, right? And that's it. I hope you read the paper. The DOI is linked there. If you have any questions, please let me know. Thank you.